Hi everyone, and welcome to today's Chemistry Daily Booster. This is number 15 in our series for paper 2, and it is advanced information listed for both foundation chemistry and higher tier chemistry. What we're going to be looking at today then are some other key reactions, and we're going to start off with the contact process. Contact process is the process we're going to use to make sulphuric acid, and there are three raw materials we need at the start. First one, sulphur. Second, air. Third, water. The contact process itself is a three-stage process, which we can see summarized in the diagram on the right. So you can see those three raw materials, sulphur, air and water, going in on that left-hand side to the different stages. So what we'll do is we'll have a look at each stage in turn to understand what happens and discuss some of those key features about the conditions we choose. Stage 1 then. Sulphur is burnt in air to produce sulphur dioxide. So realistically we add oxygen to sulphur and we make sulphur dioxide, SO2. Not reversible, quite a straightforward reaction to start. Stage 2 is a reversible reaction. Here we're going to take the sulphur dioxide and react it with oxygen once more, but this time we make sulphur trioxide, SO3. If we look to the right of the balance symbol equation, you can see our delta H is a negative value, which means that the forward reaction is exothermic. Therefore, if we increase the temperature, what we're going to be doing is moving the equilibrium position to the left, so that reduces the yield. In terms of the conditions we choose then, 2 atmospheres of pressure, 450 degrees Celsius, and a vanadium oxide catalyst. When we've got that, we produce a 96% yield. Obviously, the temperature is going to be that compromise between a high enough temperature for a fast enough rate of reaction, but not too high so as to have a negative effect on the yield. We use the catalyst in order to obviously speed up the rate at which the reaction takes place by providing an alternative reaction pathway with a lower activation energy. And because we've already got a yield of 96%, there is no value in increasing the pressure above 2 atmospheres. That would just be expense for very little gain, so we don't bother. Stage 3, if we look at it as an overview first of all, is where our sulphur trioxide is converted to the sulphuric acid by adding water. Now, the trouble with doing that as just a one hit is that it would be incredibly exothermic, to the point that actually we just create basically acid mist. Now, obviously where we have workers nearby, creating a mist of acid is pretty much stupidity, so we wouldn't do that. Instead, we break that step down into 2 smaller stages. Sulphur trioxide is passed through concentrated sulphuric acid first of all, and we make a substance called oleum. Then the oleum is added to the water, which makes the large volume of concentrated sulphuric acid. So realistically what we're doing is using a small amount of concentrated sulphuric acid to create the oleum, and then that is added to water to make a larger amount of concentrated sulphuric acid. So we are making more sulphuric acid, we just need to use a little bit in the first instance to make the oleum, so this step is safe. As we said, when we're considering the reaction conditions that we're going to choose, we do need to have that consideration between cost, safety, and of course our yields and rates of reaction. So because the equilibrium position is far to the right already, there's no point increasing the pressure dramatically. We use 2 atmospheres to move it through the converter, but that's it. No point going any higher, it would be wasted money. We mentioned the fact that the forward reaction is exothermic. We knew that because delta H was negative. Therefore, the backwards reaction is endothermic. Lower temperatures would favour that higher equilibrium yield. But we've got to have that compromise between rate of reaction, remember. And the other bit we need to consider is the fact that our vanadium oxide catalyst is only going to be functional above 380 degrees Celsius. So we can't go below 380, otherwise the catalyst won't do what it needs to. So we obviously pick on nice little compromise temperature. The second chemical we're going to look at how we make is ethanol. Now we have a couple of options for making ethanol. We can use a renewable raw material source, and that is in the form of plants. They're renewable because they're not going to run out. We can just plant some more plants. So if we're using plants as our base, we're going to carry out a fermentation reaction to make the ethanol using yeast. Now, yeast contain enzymes that will convert the glucose from our plant material into carbon dioxide and ethanol, and that gives us our little word and symbol equation at the bottom there. From the work you've done on organic chemistry in C6, you should understand how you can work out the formula of any of the alcohols, but ethanol is the key one here. Carbon dioxide you should know, glucose you should know the formula from biology. When we consider the conditions for our fermentation then, we need to be mindful that if the temperature is too low, then our yeast cells are going to become inactive. If, however, the temperature is too high, we will denature the enzymes. So we need to strike that happy medium between those two. And therefore, fermentation usually carried out at 35 degrees Celsius and normal atmospheric pressure. Altering the pressure is going to do nothing of benefit in this situation. Option 2 for making ethanol uses non-renewable raw materials. Now they're non-renewable because we're using them faster than they can be replaced, so they will eventually run out. And the non-renewable raw material in this case is ethene, and the ethene comes from crude oil. The way we make ethanol from ethene is we hydrate it. So hydration is all about adding water. Ethene plus water makes ethanol. Notice it's a reversible reaction. We know because of the reversible reaction sign. Therefore, we can choose conditions to make that more to our favour because we can shift the equilibrium position. The forward reaction we can see is exothermic because it's got a negative sign in front of our 45 kilojoules per mole. Therefore, what we need to do is consider what temperature we would want to use, because when we increase the temperature, we're going to decrease the yield. So 300 degrees Celsius is where we go. If we look at the actual moles of gas, we can see 2 moles of gas on the left, 1 mole of gas on the right. Therefore, increasing the pressure will increase the yield because it moves the equilibrium position to the right where the fewer moles of gas are. And we use a catalyst in the form of phosphoric acid in this case. They could ask you to justify the choice of a particular pathway as far as producing ethanol goes. So what we've got here is a little table of kind of key features, if you like, about the two processes, and you could use these in a comparison question. If we look at fermentation first of all, it's got a low cost of raw materials, which is a positive. It's only a moderate temperature and normal pressure, so there's no costs really associated there. Low energy requirements, but it has a low rate of reaction and a low percentage yield. The other factor is it's got a low purity, so we'd have to filter it and carry out fractional distillation before we could use it in our drinks, etc. Compare that with hydration. Cost of raw materials is high and our energy requirements are high because we need that high temperature and high pressure. However, positives. The rate of reaction is high and our yield is 95%. Plus, there are no byproducts. So that means we don't have to purify that product once we've made it. You can obviously give both sides there. If they were to ask you to evaluate, you'd have to give pros and cons and usually select which process you think at the end. But do read the question to obviously make sure you answer all parts of it. If there are bits from today's Daily Booster you'd like to go over in more detail, then you can find these videos on the C6 playlist on the channel. Obviously, you should have a revision guide that you can use to support your learning, and as always, do look at some of the past exam questions just to brush up your knowledge of what style of questions is likely to come up on this particular paper. Then don't forget to join us again tomorrow for our next Daily Booster.